Hey everyone, welcome back to the channel. Today, we're diving into a topic that's not just mind-blowing but also fundamental to our understanding of the universe: time. Time is one of those concepts that's so ingrained in our daily lives that we often take it for granted. But have you ever stopped to wonder what time actually is? How does it shape our reality, and why is it so crucial in the grand scheme of things? In this lecture, we'll be exploring time as an essential component of the four-dimensional spacetime continuum. This isn't just some abstract concept, it's a vital part of how we understand the universe around us. So, buckle up, because we're about to embark on a journey through dimensions, relativity, and the very fabric of reality itself. Our goal today is to peel back the layers of time and understand its role in the universe. We'll delve into the dimensions of space and time, explore Einstein's groundbreaking theories of relativity, and see how these ideas translate into our everyday lives through experimental evidence. Finally, we'll touch on the philosophical and practical implications of viewing time as a dimension. Understanding dimensions. First off, let's talk about dimensions. When we think about the world around us, we usually consider three spatial dimensions: length, width, and height. These dimensions help us describe the position and size of objects in space. Imagine a simple box. It has length, width, and height. These three measurements give us a complete picture of the box's physical structure. But there's more to our universe than just these three dimensions. Enter the fourth dimension, time. Unlike the spatial dimensions, time is a bit trickier to wrap our heads around. It's not something we can see or touch, but it's absolutely integral to the fabric of the universe. Time allows us to understand change and sequence events. Without time, everything would happen all at once, and causality would be meaningless. Spacetime continuum. It means that space and time are not separate entities but are interwoven into a single, four-dimensional continuum known as spacetime. This concept is central to modern physics and helps explain a wide range of phenomena, from the orbit of planets to the behavior of light. The interconnection of space and time has some mind-bending implications. For instance, time dilation means that astronauts traveling at high speeds or living in strong gravitational fields will age more slowly than people on Earth. This isn't just a theoretical idea, it's something we've observed and measured in real-world experiments. Let's look at some of the evidence that supports these theories. One of the most practical applications of our understanding of time dilation comes from the Global Positioning System, GPS. GPS satellites orbit the Earth at high speeds and experience weaker gravitational fields compared to the surface of the Earth. Both of these factors cause the clocks on the satellites to run faster than those on the ground. To ensure accurate positioning, the system must account for these differences. Without these corrections, GPS would be wildly inaccurate. Another compelling piece of evidence comes from experiments with atomic clocks. Scientists have placed atomic clocks on airplanes and in high-altitude locations and compared them to clocks on the ground. These experiments consistently show that the clocks at higher altitudes or traveling at high speeds run faster than those at lower altitudes or stationary positions. This is a direct observation of time dilation in action. Now, let's take a moment to ponder the philosophical implications of all this. If time is a dimension, just like the spatial dimensions, what does that mean for our understanding of the past, present, and future? Some theories suggest that all moments in time exist simultaneously in a four-dimensional spacetime block. This idea challenges our intuitive sense of time as a linear progression from the past to the future. On a more practical level, our understanding of time as a dimension has profound impacts on technology and daily life. from the synchronization of global communication networks to advancements in navigation and space travel, the concepts of relativity and space-time are at the heart of many technological innovations. Understanding these principles helps us push the boundaries of what's possible and opens up new frontiers for exploration and discovery. Time is not just a ticking clock but a fundamental aspect of the universe's fabric. It's interwoven with space, affecting everything from the way we navigate the globe to the way we perceive the cosmos. As we continue to explore and understand the nature of time, we uncover deeper truths about the universe and our place within it. So, next time you check the time, remember that it's not just a number on a clock. It's a glimpse into the intricate and fascinating structure of reality itself. Time travel. Let's kick off with a topic that has fascinated humanity for centuries: time travel. Is it possible to travel through time, and if so, how? According to the theory of relativity, time travel to the future is not just possible, it's a reality. As we discussed earlier, time dilation means that if you travel at speeds close to the speed of light, time will pass slower for you compared to someone who is stationary. This means you could theoretically travel into the future. But what about traveling to the past? Traveling to the past is a bit more complicated. The idea of closed time-like curves, CTCs, in general relativity suggests that under certain conditions, space-time could be warped in such a way that it loops back on itself, potentially allowing for time travel to the past. However, this leads to paradoxes, such as the famous grandfather paradox, where you could potentially prevent your own existence by altering the past. While these ideas are intriguing, they remain speculative, and we have yet to find a practical method for traveling to the past. The arrow of time. Now, let's talk about the arrow of time. The arrow of time refers to the one-way direction or asymmetry of time. We experience time as always moving forward, from the past, through the present, and into the future. This concept is closely tied to the second law of thermodynamics, which states that the entropy, or disorder, of a closed system will always increase over time. This increase in entropy gives time its direction and explains why we remember the past but not the future. But why does entropy increase? This question touches on some deep and fundamental aspects of physics and cosmology. Some theories suggest that the initial conditions of the universe at the Big Bang set the stage for this increase in entropy. The low entropy state of the early universe means that there's a lot of room for entropy to increase, giving time its forward direction. Time in quantum mechanics. Let's take a detour into the realm of quantum mechanics. In the classical world, time seems to flow continuously, but at the quantum level, things get a bit fuzzy. Quantum mechanics describes the behavior of particles at very small scales, where the classical concept of time breaks down. Instead, particles exist in a superposition of states and can be entangled, meaning the state of one particle can instantaneously affect the state of another, regardless of the distance between them. One of the most intriguing ideas in quantum mechanics is the concept of quantum time. Unlike classical time, which flows uniformly, quantum time can be thought of as discrete and probabilistic. This leads to fascinating possibilities, such as quantum time travel, where particles might jump from one time to another without traversing the intermediate states. While these ideas are still theoretical, they open up new ways of thinking about time and its role in the universe. Cosmological implications of time. Next, let's consider the cosmological implications of time. Our understanding of time is not just limited to Earth, it extends to the entire universe. The Big Bang Theory, which describes the origin of the universe, is fundamentally tied to the concept of time. According to this theory, time began with the Big Bang, and the universe has been expanding ever since. This expansion affects our understanding of time in several ways. For one, it means that the age of the universe can be measured by looking at the cosmic microwave background radiation, the afterglow of the Big Bang. Additionally, the expansion of the universe implies that time is not uniform across the cosmos. In regions of strong gravitational fields, time moves slower, while in regions of weaker fields, it moves faster. Moreover, recent discoveries in cosmology, such as dark energy, suggest that the universe's expansion is accelerating. This acceleration could have profound implications for the future of time and the ultimate fate of the universe. Some theories propose that time itself might come to an end in a big rip, where the expansion of the universe tears everything apart, including the fabric of space-time. Philosophical reflections on time. With all these scientific insights, let's pause for some philosophical reflections on time. Time is not just a physical dimension, it's also a deeply human experience. Our perception of time shapes our memories, our decisions, and our sense of identity. Philosophers have long debated the nature of time, from ancient thinkers like Heraclitus, who believed in the constant flux of time, to modern philosophers who explore the implications of relativity and quantum mechanics. One of the most profound questions is the nature of the present moment. Is the present a fleeting slice of time that moves from the past to the future, or is it an illusion, with all moments existing simultaneously in a block universe? These questions challenge our intuitive understanding of time and invite us to explore the deeper mysteries of existence. Practical applications of time understanding. Finally, let's bring our discussion back to practical applications. Our understanding of time as a dimension has revolutionized technology and everyday life. From the synchronization of clocks in global communication networks to advancements in navigation, medicine, and computing, the concepts of relativity and quantum mechanics have far-reaching impacts. One exciting area of research is in time-based computing, where scientists are exploring ways to use the principles of quantum mechanics to develop faster and more efficient computers. These quantum computers have the potential to solve complex problems that are currently beyond the reach of classical computers, opening up new possibilities in fields like cryptography, materials science, and artificial intelligence. So, there you have it, our journey through the dimensions of time, from the basics of spacetime to the cutting-edge theories of quantum mechanics and cosmology. Time is a complex and multifaceted concept that continues to intrigue scientists, philosophers, and thinkers across the world. It's not just a ticking clock or a calendar date. It's a fundamental aspect of the universe that shapes our reality in profound ways. As we continue to explore and understand the nature of time, we'll uncover deeper truths about the cosmos and our place within it. So, the next time you think about time, remember that it's not just a mundane part of everyday life but a gateway to the mysteries of the universe. Thanks for joining me on this incredible journey. If you enjoyed this lecture, don't forget to like, subscribe, and hit that notification bell for more deep dives into the wonders of the universe. Until next time, keep questioning, keep exploring, and stay curious.